Hello everyone. I welcome you all to another video of the series of lectures where we are trying to build a machine learning model for predicting the solubilities of organic molecules using moderate descriptors. Before we move ahead, let's just do a quick recap of what we learned in the previous video. We had this truncated dataset with 281 descriptors, and what we did was we defined our dependent and independent variables for building our machine learning models, and we scaled our descriptors using standard scaler so that our data is normally distributed. Then we used the sklearn's train test split method to split the data into training and test sets. Initially, we looked at linear regression model with the help of stats models, and we saw that we had good R-squared values, but most of the descriptors in here were irrelevant as suggested by the p-values. Then we talked about the curse of dimensionality with which most of these machine learning models suffer. And we also used sklearn's linear regression and random forest classes to build linear regression models and random forest model. And we saw pretty good accuracy with random forest model, although slight overfitting was also observed. We also talked about the importance of cross-validation and visualized our results with the help of matplotlib. LazyPredict is an amazing package which helped us to screen more than 40 models in just few lines of codes, and we saw that Bayesian Ridge and ElasticNet-CV were the most efficient models in predicting the solubilities of these compounds. So in this video, we are going to be talking about some dimensionality reduction techniques. The first technique is principal component analysis. Now, what is principal component analysis? The primary goal of principal component analysis is to transform the original features of a dataset into a new set of uncorrelated variables called principal components. These components are linear combinations of the original features, and they capture the maximum variance in the data. Now, what is variance? Variance basically quantifies the degree of spread or dispersion in a dataset. It provides a numerical measure of how individual data points deviate from the mean. This information is crucial for understanding the variability inherent in the data. So what we are going to do in here is that, as you know, that we have this data set with around 281 descriptors, right? So what we are going to do with principal component analysis is we are going to reduce these number of descriptors to just few. In this case, I'm just showing 2 descriptors here, but you can have 2 or 3 or 4 descriptors. And when we are using principal component analysis, the first descriptor or principal component would capture the maximum variance, and it would keep on decreasing as we increase the number of principal components. So before I show you how it can be done practically, let me give you a brief description of the PCA class in sklearn's library. So what we need to do is first we need to import PCA class from sklearn.decomposition, and it will take in a parameter as number of components. Basically, we need to put in some integer values such as 2, 3 or 4, or the number of descriptors or components that we need. And that's kind of all we need in terms of parameters. And with the help of explained variance ratio, we are gonna see the percentage of variance explained by each of the selected components. So without further ado, let's just go back to the Google Colab notebook and see how it's done. So like I said before, first we need to import PCA class from sklearn.decomposition. So let's go ahead and do that. Secondly, this is a precondition for these dimensionality reduction techniques, that we need to scale our data before we go ahead with reducing these to few descriptors or few components. So in the previous video, we have already used standard scaler to scale our data, and we already stored our data set or scale data set in scaled_df variable. So let me just print this out, and you can see this is our scale data. And let me just check the shape again so that we are sure that it's the right data. So we have 1144 data points and 281 descriptors. So next, it's very simple. We just need to create an instance of this class PCA with the n components as parameter. Here the argument I have given is 2 because I want to reduce these 281 descriptors to just 2 descriptors, and then I'm calling a fit transform method on this PCA object using our dataset. Now just to visualize it appropriately, I am converting these components into a data frame. So let's just go ahead and have a look at our reduced components. So this is principal component 1, this is principal component 2, and these are uncorrelated descriptors. Now let's just see the variance ratio. So basically it means that the first descriptor over here captures 10% of the variance, and the second descriptor over here, or second principal component, grabs the 8% of the variance in the dataset. Now what we can do with that is we can build a model and see if there is any difference. Now again, one disclaimer that this is just 18% of the variance in the data set and out of total of 100. So we cannot really expect much, but let's just see what happens if we use just these two descriptors for building our model. So again, what I'm going to do here is split our data set into train and test. I'm using the same random state, so let's go ahead and do that. And now I am using the same old stats model to build a linear regression model so that we have all the coefficients and summary of our results. So let's just run this and see the summary. Now of course, just two components here, so we have got very less r-squared value, and the adjusted r-square is quite the same. So what I'm gonna do next is I'm gonna increase the component to, let's say, just 5 components, and I'm gonna again run the model. Now as you can see here, as we have increased the number of components, the r-squared value has also increased to 0.647, and there is just a slight decrease in the adjusted r-square, and it has a value of 0.645. And as you can see here, the p-values are also 0, so that means all these descriptors are relevant. So what I'm gonna do next here is I'm gonna increase the components to 8. So let's just run this again, and obviously the total amount of variance captured by these 8 components are more than 5 or 2 components. So let's just split our data set again and use stats model to build our model. So as you can see here, with 8 components, the r-squared value has further increased to 0.731, and there is just a slight decrease in adjusted r-square, and all these descriptors here are also relevant. So this is just the training data, right? What I'm gonna do is I'm again gonna use sklearn and build a linear regression model so that we can see the R2 scores of train as well as test. Now train is gonna be the same as that of in here, 0.731, and let's see what the test results give us. So of course this is 0.731, same, and for the test as well, we don't really see any overfitting. Now if we go up in here where we use 281 descriptors, you can see over here, although r-square is pretty good for the training set, but for the test it has drastically decreased. So there was a lot of overfitting in here, and with our reduced number of descriptors, we can see that the overfitting has reduced to a greater extent. Now let's just see with the help of random forest as well. So in here the results are pretty similar as above using the 281 descriptors. So in here we have got 0.98 for training and 0.86 for test, and in here as well the results are more or less the same. Again, that does not mean that if you use principal components, you're not gonna see overfitting in any of the models. Each and every model is different. Random forest models or tree based models are known to overfit. So there are many other things you can do to reduce overfitting, and we can hyperparameter tune and all that stuff, and we are going to be talking about those in our future videos. But the point here is that we can reduce the number of components here, and one thing we can do is we can build model using these components. And one more thing that I want to point is that if you just don't give any component, let's say I'm giving none here. Now in here you can see we have 281 principal components, and basically you can just rank them in the order of variance. The first component would capture the most of the variance in the data set, and as we move on, the variance level would decrease. And in here at the end you can see the last component, which is 281st. It's just 9 into 10 raised to the power minus 34, so that's very less. So these are basically irrelevant. We can just not use this. So the threshold is in your hand. It depends totally upon you that how many principal components you want to use for whatever you are trying to do. So this is one thing that you can do here. Another thing is you can use these principal components to visualize in a lower dimensional space. So let me just talk about it in detail using tSNE. Like principal component, tSNE is another technique by which you can reduce the number of descriptors. I am on the official tSNE documentation of sklearn, and here in order to use this we need to import this tSNE class from sklearn.manifold. In here you can reduce to just 2 tSNE components in contrast to principal component analysis, where you can have as many principal components as the number of descriptors in your data set. And this is mainly used to visualize high dimensional data. It converts similarities between data points to joint probabilities and tries to minimize the Kullback-Leibler divergence between the joint probabilities of the low dimensional embeddings. So let's just see how it works. So what I'm gonna do is import this tSNE class from sklearn.manifold. In here as well we need the scale data, and the number of components is 2. We cannot exceed that, so I'm creating an instance of this class with 2 as an argument, and I'm calling a fit transform method using our scale data set. And of course we want to visualize it as a data frame, so that's what I'm doing in this line of code. So let's run this and have a look at our data set. So these are the 2 tSNE components that we have got. Now it's obvious that when we had these 281 components in our scale dataset, we can't really visualize all these components in a 2-dimensional space. But when we have these 2 descriptors or components, we can plot these, one on x-axis and one on y-axis. So let's just go ahead and first plot just these 2 components as a scatter plot using matplotlib. So that's what I'm gonna do here. And yeah, let's just run this. So this is tSNE component 1 on x-axis, and this is tSNE component 2. Now of course these are non-correlated descriptors, so you're not really gonna see any type of correlation. So what's the use of this, right? We don't really get any information out of this. So what I'm gonna do here is that I'm just first gonna show you our target here. Now this is our target, which is Meyer log of solubilities. Now we are dealing here with the regression problem, right? And what I'm gonna do is I'm gonna take a median of this. So the median is minus 2.8. So what I'm gonna do is I'm gonna convert this column with continuous values into 2 classes. Basically compounds with solubility values less than minus 2.8 would be considered less soluble, and compounds with value greater than -2.8 would be more soluble. So basically I'm going to be converting these numerical values into two descriptors, two labels, less soluble and more soluble, but computer is not really gonna understand this more and less soluble thing. So we need to convert these into numbers, zeros and ones. So what I'm gonna do in this line of code here is I'm gonna convert these more soluble labels into ones and less soluble labels into zeros. So what I'm doing here is that I'm using a map function and I'm mapping this lambda function on this y variable here, and if the values in our y column is greater than -2.8, it would return true, and if it's less than -2.8, it would return as false. And in here I'm just converting these true and false into integers here, basically 1 for true and 0 for false. So I'm storing these as a sol underscore CLS. Now let's just run this, and I'm importing a counter function from collections to show you how many zeros and ones are there in our sol underscore CLS. So we have, so out of 1144 values, we have 558 ones or more soluble compounds and 586 zeros or less soluble compounds. So our data set is pretty balanced. Now what I'm gonna do is I'm gonna use this variable as a color map. So in here I'm basically gonna color these scatter points based on these classes. So that's what I'm just doing here. So let me just run this. Okay, so you can see we have kind of clustering here. These blue dots represent more soluble compounds, and yellowish points represent less soluble compounds. Now you can see here, although it's not quite efficient, but you can see these less soluble compounds are kind of clustered in some places here, and all these more soluble compounds have a kind of different clusters. Although again, I'm not saying it's a perfect clustering, but you get the idea that you can use these tSNE components for clustering and visualizing your data set in a lower dimensional space. So that is it for now. In the next video, I'm gonna be talking about a very interesting topic of feature importance. Basically, if you remember, we built this random forest model, and we are gonna be using feature importance algorithm to extract important features responsible for building these models, and we are gonna see if we can use those few descriptors to make this model, and we're gonna see how those descriptors affect the R2 score and our predictive abilities of the model. So in this manner, we can build a interpretable models rather than a black box model. So stay tuned for that, and thank you for watching.